All right, so welcome everybody. My name is Silviu. I'm supposed to tell you about the space of CFTs. I'll be splitting this series of lectures with Zohar Komargadsky. I'll do the first three and he'll do the last three. So let me write space of CFTs. CFT stands for conformal field theory. So I should say from the beginning that I apologize if this is very introductory. CFT stands for conformal field theory. Conformal field theories are special types of quantum field theories. So the first thing I want to say is what is quantum field theory and what it's good for. Quantum field theory is a framework for solving certain problems in various areas of physics, in particular in statistical physics, in condensed matter physics, and in particle physics, and beyond. In statistical physics and condensed matter physics, quantum field theory is a good framework close to phase transitions. So this is good, close to phase transitions. Otherwise, we have a system on a lattice, and we have to diagonalize the lattice Hamiltonian. And the phase transitions are driven by, for statistical physics systems, they're driven by thermal fluctuations, and for condensed matter systems, they'd be quantum phase transitions, they'd be driven by quantum fluctuations. Okay. So the phase transitions driven by thermal fluctuations are described by quantum field theory in Euclidean signature, and the phase transitions driven by quantum fluctuations are described by quantum field theory in Lorentzian signature, where usually in Lorentzian signature there's a quantity that we call the speed of light, and in condensed matter systems that speed of light is usually an emergent property at lower energies. Okay, so this is quantum field theory. This is what it's good for. What are conformal field theories? Conformal field theories are special quantum field theories that, in addition to being either, so maybe I should mention here, so this is for in Euclidean signature and this is in Lorentzian signature. So conformal field theories are special quantum field theories that, in addition to being invariant under either rotations or Euclidean theories or Lorentz transformations, they also have an additional symmetry, so also possess two other symmetries. So symmetry under dilatations, well, that means that they're invariant under rescaling all the coordinates. This is x goes to lambda times x. And they have another symmetry. So lambda here is just a parameter. And they're also invariant under special conformal transformations. Which are a little bit more complicated. Dilatations are parameterized by a scalar parameter, and special conformal transformations are parameterized by a vector parameter. So I'm just going to write it, but I'm not going to use it. So x goes to x minus b times x squared divided by 1 minus 2 b dot x plus b squared x squared, where b is a parameter. So far I've just been defining my terms. So hopefully it's clear why we might care about quantum field theory. Quantum field theories in statistical physics or condensed matter physics are good for describing phase transitions. If we have phase transitions, we might want to use quantum field theory. But why would we want to care about conformal field theories, which are these special types of quantum field theories with weird properties? Well, the reason for that is that in this context, in the context of phase transitions, they are good descriptions of critical points also referred to as second-order phase transitions. Okay, and I will explain what this means in a bit. This is what today's lecture will be about. Another thing that I should say about them that's going to be very important is that because they're invariant under dilatations, you can rescale the coordinates and the theory is the same. That means that these theories don't have an intrinsic length scale. There's no intrinsic length scale. And we'll see that this is precisely what happens at critical points. The length scale that would otherwise be in the system blows up as we go to the critical point, and the system no longer has an intrinsic length scale. And they have many other properties, and these properties will be described in, well, at least some of them will be described in Chris's lectures after this one. Okay? So, any questions about this? So what I want to focus on is phase transitions in statistical physics. And then Zohar will talk about phase transitions in condensed matter physics, and also talk about CFTs and particle physics. So focus on phase transitions in statistical physics. So I want to have two goals. The first one is to give you some examples. And the second one is to tell you in these examples which CFTs. Why is it that they can be described, these critical points or second order phase transitions can be described by conformal field theories, and which ones? Okay. So the first phase transition that I want to talk about is about magnets. Hopefully everybody knows what a magnet is. So the way I want to think about it, we just have some piece of magnet. It has some magnetization. We could take this magnet and put it in a magnetic field. I'm going to call the magnetic field H, because this is the magnetic field that doesn't change when we go into the magnet. And I want to think of this as the temperature T. Okay? So the procedure is the following. Fix the temperature, apply a magnetic field, measure the magnetization. Of course, we're usually used to seeing magnets at room temperature. So what I'm going to be describing may not be entirely familiar from a day-to-day experience with magnets, but it's still true. Okay? And there are several kinds of magnets. So the simplest kind of a magnet, from a theoretical point of view, I guess, is where the individual magnetic moments, let's call that mu, are preferred to be oriented along a certain axis. So are oriented along a certain axis. Let's say the z-axis. It's just because there's a lattice of magnetic ions, and the interactions between the ions make them such that they prefer to have the spins oriented along a certain axis. And this is what's called the uniaxial magnet. And this is what I'll talk about in more detail. And what I want to do with this magnet is apply a magnetic field precisely along this axis. I'm not going to ask about what happens if we apply a magnetic field perpendicular to this preferred axis. There are also more complicated types of magnets where, if we have a type of magnet where the spins prefer to be aligned along a certain axis, we can imagine we have some other material where the spins prefer to be aligned in a plane, anywhere in a plane, or we have another material, could have another kind of material where the spins can be oriented in any direction in space in 3 dimensions. So these other examples where mu can be oriented in a plane. This is called an XY magnet because the spins can just rotate in the x and y directions. And mu, another type of magnet, is when mu is in any direction. And these are called Heisenberg magnets. Okay. So of course, these magnets have some symmetries that are going to be worth keeping in mind. So the uniaxial magnet is symmetric under flipping the z direction. So if we apply a magnetic field in the positive z direction, the effect should be similar to that when we apply the magnetic field in the negative z direction. Essentially what happens is the magnetization just flips. So this symmetry is a Z2 symmetry. The XY magnet has a symmetry under, if the spins can rotate anywhere in a plane, then it shouldn't matter how we orient the magnet if we rotate the magnet within that plane. So this one has a symmetry under rotations in a plane. So this is an O2 symmetry. And the Heisenberg magnet has this rotation symmetry in 3 dimensions, because it doesn't matter in which directions the spins can be oriented. So if we apply a magnetic field, it shouldn't matter in which direction we apply the magnetic field, we should get the same magnetization in magnitude. So this would have an O3 symmetry. Okay? Good. So what can we do with these magnets? Well, we can observe what happens. So apply this procedure, fixed temperature, apply the magnetic field, measure the magnetization. What do we see? Okay? And this is what we see. For the temperature smaller than some critical temperature, so this is critical temperature. And this is probably what everyone has seen when playing with magnets, is that when we play with a magnet, we don't apply a magnetic field to the magnet, but it still has a magnetization. So for T smaller than Tc, the preferred state has, at zero magnetic field, has non-zero magnetization. And this thing, you just have to believe me that if you heat up the magnet, this is going to stop being true at some temperature Tc. So for temperatures bigger than Tc, the magnetization is 0 when H is 0. So essentially, we can just plot this. If we plot the magnetic field and the temperature, there's some region over here up to the temperature Tc where there's a non-zero magnetization. The non-zero magnetization that we have at zero temperature, at zero magnetic field, depends on how we built the magnet. So if we first apply some magnetic field and then we reduce the magnetic field to 0, then the magnetization will point in the direction in which we applied the magnetic field. Okay? So in this region, this magnet is a ferromagnet. And I'm drawing this. It's good to have a picture. And it's going to be this point here at Tc that's going to be described by a CFT. And I'll explain exactly which CFT it is. Okay? So I want to make a note that criticality, namely being at Tc, being at this point, requires setting H equals 0 and T equals Tc. This might seem a little trivial, but it's very important. What this means is that in order to reach this point, we have to tune two parameters. We have to tune the magnetic field to 0, and we have to tune the temperature to the critical temperature. Okay? In this case, for a magnet, tuning H to 0 is easy, because the magnet has a symmetry under H goes to minus H. So we should just set, if we want to tune H to 0, we should just set H to the value that's invariant under the symmetry. H goes to minus H. Okay? So it's 0 because H equals 0 is special. But for more general systems, this may not be the case. Erasing the blackboard is hard work. So I want to tell you what happens in more detail as we apply a magnetic field. So now I want to make a different plot where I plot, so here I only plotted the magnetic field as a function of temperature. I want to plot the magnetization as a function of the magnetic field. So M is a function of H. Maybe I want my axis to be over here so that I have more room. So what happens for temperatures smaller than the critical temperature, so when we're in this region, and I'm thinking of fixing the temperature. The magnetization as a function of the magnetic field looks like this. So for positive magnetic fields, we have positive magnetization. For negative magnetic fields, we have negative magnetization. So this is all for the uniaxial magnet. So I'll focus mostly on the uniaxial magnet. Okay? This discussion can be generalized to the other kinds of magnets. And the value, so this is for T smaller than Tc. And this value here is called spontaneous magnetization. And is the magnetization of the magnet that you see at if T is the room temperature. This is a magnetization of the magnet that you see. So what happens for T bigger than T critical? If we plot the magnetization as a function of the magnetic field, well, it should go to 0. As I said before, it should go to 0 when the magnetic field is 0. So T bigger than Tc. So we'll just do this. So the question is, what's going to happen at exactly at the critical temperature? I'm going to draw this plot here. So this is at T equals Tc. Well, we have to go from this picture to that picture. And the way we do that is that this line becomes vertical here. The tangent to the curve becomes vertical. Okay? So this is right at the critical temperature. Okay? Are there any questions about magnets so far? So the interesting thing that happens in the system is the transition between the two regimes, the ones below Tc and the one above Tc. And it's this region around Tc that can be described with quantum field theory, and that I'll talk about more. So close to Tc, there's a thing called scaling behavior. So let me try to explain what this means. It can be seen in various quantities, and I'll just make a list of what quantities exhibit the scaling behavior, or at least the standard ones. So the notion that comes along with this is that of critical exponents. And in order to define them, let me define a dimensionless quantities. So I'll define a ratio little t, which stands for temperature. So this is T minus T critical divided by T critical. And then there's another one for the magnetic field, little h, which is capital H over Kb times the temperature, times the critical temperature. Okay? So these are just some dimensional quantities. Kb is the Boltzmann constant. So the first example in which we see scaling behavior is for the specific heat. And this defines a critical exponent called alpha. So it's observed that the specific heat at h equals 0, so for 0 magnetic field, looks like this. So C, by definition, is the second derivative of the free energy with respect to temperature. I'm going to, well, okay, so I can just write down the temperature here. And this behaves as a power of this parameter little t. So if we set h to 0, the only thing we have is little t. And what's observed is that this behaves as a power of little t. So it's usually denoted by t to the minus alpha. So this diverges if alpha is positive. So the region close to the critical point is described by all sorts of quantities like this, that when we set either h to 0 or t to 0, various quantities behave as powers of the other one that we didn't set to 0, and the powers can be quite non-trivial. So let me try to write another one. Beta, this is the spontaneous magnetization. And this would be the limit when h goes to 0, say 0 from above, of the magnetization. So it's this quantity here. And we see how it behaves as a function of temperature. And it goes like, of course, this only exists for t smaller than Tc, and this behaves as minus t to the power beta. So that's the definition of beta. Let me do more. Another one is gamma. So we're going to go through all the Greek letters. So this is the zero field susceptibility. So this is chi, which is the derivative of the magnetization with respect to the magnetic field evaluated when h is 0. And this goes like t to the minus gamma. So that's the definition of gamma. This also diverges if gamma is positive as we go to the critical point. So far, all of them have been in terms of t. Let's just do one in terms of h as well. So that's delta. Right at the critical point, at t equals Tc, the magnetization itself goes like a power of the magnetic field. So this is, the power is called 1 over delta. There are more complicated ones. Nu, there's two more that I want to mention. which describes, the other two describe correlations. So we have a magnet. The magnet has some spins, maybe arranged on a lattice. The spins have magnetic moments. But we can try to see if the spins are correlated. So we can construct the correlation function of the spins. Let's just call that g of r. So this is the expectation value of the spin at some position r and spin at 0 minus the average value of the spins. The spins are just proportional to the magnetization. The expectation value of S is proportional to the magnetization. So minus this squared at h equals 0. And of course, we have that S, the expectation value of S is non-zero for t bigger than t, for t smaller than tc. And the expectation value of S is 0 for t bigger than tc. So away from tc, so not quite at t equals tc, how does this behave as a function of position? So what this is measuring is like, if the spin here is up, so these spins could be up or down, like say plus a half or minus a half. So if the spin here is up, then how likely is it that for the spin at some distance away will also be up? Okay, so for t bigger than tc, then this correlation function g of r decays exponentially. So it's proportional to e to the minus r over some quantity called c. And this is the correlation length. And what happens as we approach the critical temperature is that the correlation length gets bigger and bigger. And right at the critical point, it blows up. So the correlation length, c, is proportional to absolute value of t to some power, and that power is denoted by minus nu. So this is what I was saying before, that CFTs are quantum field theories with no intrinsic scale. And in this case, we actually see that as we approach the critical point, the scale in the system, which is the correlation length, goes to infinity, so it disappears. So it's reasonable that the critical point itself can be described by a conformal field theory. And another exponent that I want to mention, and this is, I promise, the last one, is that right at t equals tc. So here I discussed how the correlation between the spins behaves away from t equals tc, but right at t equals tc, it also behaves as the power of the distance, and that power is related to this exponent eta. So g of r is proportional to 1 over r to d minus 2 plus eta, where d is the number of dimensions. So for us, it would be d equals 3. Okay? Are there questions about this?
I have a simple question.
Yes.
When we say that the only length scale in the system is usually correlation length,
Yes.
why do we always forget that there's a lattice size? Just because we can absorb it to the definition of the spins and that's it?
Presumably at large distances, the lattice, the fact that there's a lattice size, there's a lattice separation is not that important.
That length disappears.
Right. Right. If we measure these quantities, they're not sensitive to the lattice spacing. And of course, when we say that the correlation length c goes to infinity, well, what I really mean is the correlation length in units of the lattice spacing. The lattice spacing is gonna come up. Other questions? So that's one example of a system that has a second-order phase transition. And for that second-order phase transition, we can define these critical exponents. Let me give another example. That other example is water. People are hopefully familiar with the phase diagram of water. So we have pressure and temperature. And it looks sort of like this. So here we have the solid phase. I think it's called ice. This is the liquid. This is usually called water. And this is the vapor phase. And everybody should be familiar with the fact that if we heat up the solid, it turns into liquid. If we heat up the liquid, it turns into vapor. But if we go to larger and larger pressures, at some point we're going to stop seeing a distinction between liquid and vapor. This fluid is going to go from something that looks like a liquid to something that looks like a vapor continuously. And the point where that ends is called the critical point. And this is described by a CFT. And just to orient you, the temperature for it is 647 Kelvin, and the pressure is 374 atmospheres. So no wonder you haven't seen this. Okay? So again, let me try to draw more pictures, and maybe they'll become similar to the ones that I showed you for the magnet. So what you should be comparing this to, you should be comparing this line here that ends at the critical point with the plot that I was making before with the magnetization and the temperature, and there's a line that ends over here. So this line is analogous to that one. Okay? So if I make another plot, which is the pressure as a function of the density, it looks sort of like this. For temperature smaller than the critical temperature, it looks like that. So this is for T smaller than Tc. These curves are called isotherms. Above the critical temperature goes like that. Right at the critical temperature, we have to go from a picture that looks like that to a picture that looks like that. So this is right at the critical temperature, T equals Tc. So this is very similar to what happened with the magnetization in a magnet. As we were varying the magnetic field. So the analogy is that, well, temperature is like temperature in both systems. The pressure minus the critical pressure is like the magnetic field. This is the thing that we need to vary in order to see the analog of the spontaneous magnetization. And rho minus rho critical is like the magnetization. And by analogy, we can define for this, for water as well, critical exponents. And for instance, the specific heat goes like T to the minus alpha, rho liquid minus rho gas, goes like, so this is the analog of the spontaneous magnetization. This goes like minus T to the power beta. And we have the susceptibility. This would be the isothermal susceptibility, goes like T to minus gamma, and so on. Okay? So what's really neat about this is that we can do these experiments and we can measure these critical exponents. And surprisingly, they're actually the same for the uniaxial magnet and for this water vapor critical point. So observe same values of the critical exponents, alpha, beta, and so on, as for the uniaxial magnet. I will tell you what these values are in a bit. I mean, they're just some numbers. They're probably not very intuitive. They're not nice numbers like a half or anything. They're just some weird numbers. Okay? So then we say, maybe all second-order phase transitions are described by the same numbers. But that's not true. Because I introduced other examples of magnets. So, for instance, XY magnets. These ones will have different critical exponents. They also have critical exponents, and they're different from the uniaxial magnet or from the water vapor phase transition. And have these 3D Heisenberg magnets, which have yet another set of critical exponents. So not all second-order phase transitions have the same critical exponents, but certainly there are some that do. And because there are some that do, that requires an explanation. That means that this isn't some weird property of the system where we have to know the lattice Hamiltonian and where the lattice spacing is important, and the precise interactions between the spins are important. These are some universal properties that we can hope to understand. And I guess this is a situation that's better than in most areas of physics. So usually what we do, we just have a system and we try to understand it. We make an approximation. We compute something. It sort of matches with the experiment, but then in order to get a better approximation, we have to improve our model, and then if we improve it even more, then we get an even better approximation, right? So this is what usually happens. In this case, it seems that, at least from these examples that I gave you, that it doesn't matter what kind of system we're looking at. At some level, it doesn't matter. I mean, there are some differences between the uniaxial magnet and the XY magnets, but at some level, if the water vapor critical point has the same critical exponents as the uniaxial magnets, then maybe it really doesn't matter precisely what system we're looking at. So we don't have to be as precise in our model and still get perfect agreement, right, with the experiment. So this is why CFTs are good. Questions about this? So I just showed you some examples. Now I want to try to describe these examples with some formalism. So talk about describing critical points or the region nearby with quantum field theory. So in QFT, when people usually study QFT, we have a Lagrangian that depends on some fields and some couplings. So these are fields, and these are couplings. Of course, it is possible to define quantum field theory without referring to a Lagrangian, and this is what the conformal bootstrap program is about at some level. But we can still learn a lot from having a specific Lagrangian and studying it. Okay, so in these lectures, I'll just restrict to quantum field theories that have a Lagrangian description, for which we know the Lagrangian. Okay, and the coupling constants, just to put things in perspective, there are things that we can, they're parameters in our theory, so they're things that we can change. And so they're like this dimensionless magnetic field that I define, or the dimensionless temperature. So just to remind you, this was the magnetic field over Boltzmann constant times Tc, or like the dimensionless temperature, T minus Tc over Tc. So this is what the coupling constants will correspond to. Now, in quantum field theory, there's this thing called RG flows. And people probably have seen examples of RG flow diagrams, and an example of an RG flow diagram looks like this. So this is, say, one coupling G2, and this is another coupling G1. And so these are pictures that you've probably seen when you took quantum field theory. And they look like this. For instance, this is just an example. Oh, okay. Sorry, I didn't mean to draw it like that. I wanted to have outward arrows. Okay. So there are pictures that look like this. There's some lines with arrows on them. And at some point, some lines intersect, and that's called a fixed point. And just to put things in perspective, it will be the fixed points that will be described by CFTs. Well, hopefully that will become clear. So the question is, what do these diagrams mean? So there's some lines, and with arrows, those are flow lines. And what do they show? So the flow lines show how the couplings GA change as we coarse grain. So suppose we have a system with a lattice, and we're interested in measuring something at very large separations in the units of the lattice spacing. Now, suppose we have some spins on the lattice. Now, suppose that we take a block of spins, say a 3 by 3 by 3 block, if we're in 3 dimensions, and we want to replace this by some effective spin that's in the center in such a way that the things that we compute at very large distances don't change. In order to do that, if we do that, we should adjust what these coupling constants are. And this is what the RG flow diagram is doing. It's just saying how we adjust the couplings as we change the lattice spacing. So if we send, for instance, A to B times A, where B is a constant, in the example that I just gave, B was 3. So instead of having like 1 unit, we have like 3 units. The new lattice spacing is 3 times the old one. And this A is the UV cutoff, or the lattice spacing, with B bigger than 1. So we do this procedure, then we have to adjust the couplings GA as we do this procedure. And it's good to think in terms of infinitesimal rescalings of the lattice spacing. So if we take B to be 1 plus something I call delta L, where delta L is small, then we just have to change our coupling constants by only a tiny bit because we just did a very small rescaling. So this delta GA by delta L is going to be non-zero. And by convention, this is denoted by minus beta of G. So it's a function of all the coupling constants. So the way this particular coupling constant GA changes could be a function of all the other coupling constants. And that function is conventionally denoted by minus beta of G, and beta is called a beta function. Okay? So this beta function here is a vector field in the space of couplings. And it's what's being plotted in the RG flow diagram. So this is what this diagram means. If we're, for instance, somewhere here, and we change our lattice spacing by a tiny bit, then we have to go to, a little bit in the direction of this flow line. You see, people have taken quantum field theory? Yes? Okay, good. This is somehow just one of the parts in quantum field theory that's very confusing. And the fact that it's very confusing is unfortunately never going to change. It's one of the things that stays confusing. Anyway, so what happens at the fixed points? At the fixed points, the lines meet. So there's no direction in which to go. Therefore, as we change the lattice spacing or the UV cutoff, the parameters, the G's, don't change. So the fixed point has beta A of G, and I'm going to call the fixed point values G star equal to 0. Fixed point is the vanishing beta function. And it's at this fixed point that, as we change the lattice spacing, nothing else changes. So the theory has scaling variance. And I said before that the theories with scaling variance that also are invariant on these special conformal transformations are CFTs. So it's not that surprising that these fixed points could be described by CFTs. I haven't shown to you that at these fixed points, the theories are also invariant under special conformal transformations. And I don't think there's a very good proof of that. but it's true. Okay? So now the question is, so as I said, the quantum field theory is good for describing the phase transitions and the region close to the phase transition. So it would be good to understand what happens close to this fixed point as well, but not too far away. Okay? So very close to a fixed point, what's going to happen? Well, the beta functions must vanish right at the fixed point, so close to the fixed point, they're probably going to be linear, and the difference between the couplings and their fixed point values. So probably what's going to happen is that beta A is approximately minus some sum over B, some matrix of numbers YAB times GB minus the fixed point value, which I'll call GB star. Because right at the fixed point, we want beta to be 0. Now, it's not nice to have a matrix. It would be better to not have a matrix, to just have a number. So what we can do is to diagonalize this matrix by redefining our couplings. So diagonalize this matrix YAB. Of course, if we diagonalize it, we have to redefine the couplings GA, take linear combinations of them, at least close to the fixed point. And then this equation will look like beta A is going to be approximately minus YA, little y, which is an eigenvalue of capital Y, times GA minus GA star. So if we choose our coupling constant smartly, then the beta function for the coupling A is only related to, at least very close to the fixed point, the GA minus GA star. Okay? What that means is that, so if I put this equation, if I combine it with that equation, I can write delta GA by delta L is approximately equal to YA times GA minus GA star. Of course, on the left-hand side, it's a derivative, so I could have subtracted GA star from it. So delta GA minus GA star by delta L is given by this. So that's a differential equation. We can solve the differential equation. We can get that GA minus GA star. So remember that this DL was related to B. So you can get that GA minus GA star is proportional to B to the YA, at least close to the fixed point. Okay? You should think about YA as, this G that I define as some dimensionless number, but it comes from some dimensionful coupling. And you should think of YA as the mass dimension of the coupling. Okay? Maybe this will become clearer. It matters whether these YAs are positive or negative, because if the YAs are positive, then we go, maybe I shouldn't have erased this diagram, which looked like this. So if YA are positive, that means that as we coarse grain, we go away from the fixed point, because this thing here would take us away from the fixed point. So if we start, for instance, in this direction, and we coarse grain, we would go away, we'd get away from the fixed point. So that means that this coupling is relevant. So the RG takes us away from fixed point. And if YA is 0, that's called marginal. I won't talk about that. If YA is negative, that's called irrelevant. That means that as we coarse grain, we get closer and closer to the fixed point. So RG takes us to fixed point. Okay? This is very important because in order to describe a second order phase transition, or the region close to a second order phase transition, we want to stay close to it. So if we somehow have relevant couplings, they would have to be tuned to stay close to fixed point. So for instance, in the example of the magnet, there were two relevant couplings, H and T. As I said, in order to reach the critical point, we had to tune both H and T. Or like for the water vapor critical point, we have to tune the pressure and the temperature. But if the couplings are irrelevant, then we shouldn't worry about fine-tuning. Are there questions about this? So just to put things in perspective and make it a little bit clearer what Chris is going to talk about, is that I'll explain this. Is that these YAs are related to scaling dimensions of operators. So if in the Lagrangian we have a term that looks like GAOA for some operator O, then this operator has a scaling dimension. So this is about the CFT, right, at the CFT fixed point. So this has scaling dimension delta A. And the relation between them is that YA plus delta A is equal to the number of space-time dimensions. I think Chris will talk a lot about these delta A's. So when he says delta A's, you should think these Y's. Okay, I will explain this in a bit. But before that, I want to show you that this is actually a great framework to describe critical exponents, to calculate critical exponents. And let me explain why. So, good framework for critical exponents. And let me show you how to relate them to the y's. So suppose we want to describe these uniaxial magnets that I talked about, then so for uniaxial magnets, little t and little h were the only relevant couplings. We know this experimentally because these are the only two things that we have to tune in order to reach the critical point. And the critical exponents follow from consistency with the renormalization group. It's actually very easy to see that. Well, suppose that little f is the free energy density. What happens? The question is, what happens with it during the RG flow as we change the lattice spacing? Well, my claim is that f goes to b to the d times f, where d is the number of space-time dimensions. So if we send a to b times a is the lattice spacing. And the reason for this is that you should think about the free energy density as the free energy divided by volume. This is proportional to the free energy divided by the number of lattice sites. As we increase the lattice spacing by a factor of b, we're decreasing the number of lattice sites by a factor of b to the d. Therefore, the free energy density gets multiplied by b to the d. It's like dimensional. It's like a very, very simple argument. And we know that h goes to b to the yh times h, and t goes to b to the yt times t. That implies that the magnetization, which is the derivative of the free energy with respect to the magnetic field, goes like, so the magnetization is the magnetic moment per unit volume, so it's the derivative of the free energy density with respect to the magnetic field. So this goes like b to the d minus yh times the magnetization, because f gets a factor of b to the d and h gets a factor of b to the yh. And then all these critical exponents follow from requiring that the left-hand side and the right-hand side should scale in the same way as a power of b. So let me show you how that works. And this is going to be an amazing prediction. So for instance, for alpha, C goes like second derivative, by definition, is the second derivative of f with respect to the temperature at h equals 0. So if we see how that scales under Rg, we get that this is b to the d minus 2yt times c. Now, this c can only depend on h. So the only possibility is that c goes, c is at h equals 0. So it can only depend on the absolute value of t. So we should write c which is proportional to t to some power, and the power should be such that we get the same power of b under scaling. So that power would be this power divided by the power for t. So it would be d minus 2yt over yt. And the definition of this was that this is t to the minus alpha. So we found alpha. Alpha is 2 minus d over yt. Now, how about the spontaneous magnetization? So the spontaneous magnetization at h equals 0, the magnetization scales like b to the d minus yh. So this m should depend also on t, minus t to some power. And the power should be such that we get the same power of b. So it would be d minus yh divided by the power that's required for t. So this would be d minus yh divided by yt. And this is what we called minus t to the beta. So that means that beta is equal to d minus yh divided by yt. And I can keep going. Let me do another one, and then I'll stop. Well, then I want to mention one other thing, and then I'll stop. So the susceptibility goes like dm by dh. And also by the scaling, it goes like b to the d minus 2yh times the susceptibility. Because m goes like b to the d minus yh, and we have another yh in the denominator. So that means that chi goes like the temperature to the power d minus 2yh over yt. And we call that power minus gamma. So that means that gamma is 2yh minus d over yt. Is it clear how to play this game and compute all the critical exponents this way in terms of yh and yt? So you can do the same thing and get that delta is yh over d minus yh, and so on. You can get the other ones. I'll explain the other ones tomorrow. So now let's just look at actually, so this is an amazing prediction. It just says that all these critical exponents depend on only two numbers, yh and yt, because d is fixed to 3. So we can actually look at the measurements and see if that's true, right? So just make a table, experimental data, the exponent and the value, and that's measured. So d equals 3 for the uniaxial magnet. So alpha is about 0.11, beta is about 0.33, gamma is about 1.24, delta is about 4.8, eta is about 0.036, and nu is about 0.63. And use two of them, try to solve for yt and yh, and then plug it in to see if the others match, right? And you can do that, and they indeed match. And you get that yt is approximately 1.59, and yh is approximately 2.48. As I was saying before, these y's are related to scaling dimensions. So that means that there's some operator that couples to t. So we have the scaling dimension of the operator that multiplies t in the Lagrangian. So delta is, in this case, 3 minus y. And we get that this is approximately 1.41. And delta OH is approximately 0.518. So this is a prediction that, so the same is true. By the way, these numbers are true for both uniaxial magnets and the water vapor critical point. So the claim is that uniaxial magnets or the water vapor critical point are described by a CFT with only two relevant couplings, T and H, where the operators OT and OH have scaling dimensions these. So what remains to be done is, can we compute them? And hopefully this is what this school will be about. Okay, sorry for going over time. We'll pick up from here tomorrow. Right.
So, Silviu, can I ask you, please repeat the question?
Yeah.
It's not being recorded.
Good.
So the free energy scales like D and it doesn't get corrected.
Right.
Like naively, if I was doing quantum field theory and I was writing down the like an expression for the free energy in terms of the bare field, well, those bare fields are going to get anomalous dimensions and so on. So, I mean, ultimately, the consistency check that you did, you matched it with experimental.
Right.
Why is it that the free energy that I use doesn't get corrected?
Okay, so the question is, why is it that the scaling of the free energy under RG is so simple and it doesn't get corrected? Just the free energy density gets multiplied by B to the D. The answer for that is that the energy is a conserved quantity, and that's what makes the scaling not be corrected. Indeed, if we write down the free energy as a function of the fields and the couplings will scale in some way, complicated way, and the fields will scale in another way that's also complicated, but they combine together to give something that that scales like B to the D.
I propose we leave the remaining questions for coffee break.